So let me say welcome to everyone who's tuned in for the final seminar of the series for the spring semester. And we have saved one of the best for last, Professor Máire O'Neill. And I didn't quite get that, but I hope it's close. It is a lovely Gaelic name that I tripped over there. But Professor O'Neill is the Regius Professor at the Queen's University in Belfast, Northern Ireland. She's also the Director of the Center for Secure Information Technologies. She has a whole lot of recognitions and awards, including Royal Academy of Engineering Silver Medal. She has been in this field for a while, is known for work in electronics and cryptography in particular. But she's going to talk to us today about securing connected devices, challenges and opportunities. And before she starts, let me remind everyone, if you have questions, please post them in the Q&A, not in the chat. And with that, Professor O'Neill, the floor is yours.
Thank you. Thank you so much for the introduction. So let me go ahead and share my screen here. So I hope you can all see that. Okay, so I really appreciate the invitation to come and speak to you all today as part of your seminar series. And I will begin my talk just by firstly introducing my research institute, the Centre for Secure Information Technologies at Queen's University Belfast, and just a little bit about what we do at the institute. So CSIT was established in 2009 as the UK's National Innovation and Knowledge Centre for Cybersecurity Research. And we've enjoyed over £30 million in external investment over the first two phases of the first almost or over 10 years in our existence. And we're currently entering a third phase of investment. So we've had numerous awards within the UK and recognition for the work that we've done within our centre. Since then, including in 2015, a Queen's Anniversary Prize for the work that we've done in sort of strengthening global cybersecurity and our work and our research. Our original founder, Professor Sir John McCanney, was awarded a knighthood in 2016, and the Institute was also awarded a Regius Professorship back in 2015-16 as well, and I currently hold that professorship. We also recognised by our National Cybersecurity Centre, the NCSC, as an academic centre of excellence in cybersecurity research, and indeed more widely we're also recognised by them in terms of our cybersecurity education portfolio as well. So the mission of our centre is to couple major research breakthroughs in the field of secure information technologies with a unique model of innovation and commercialisation to drive economic and societal impact. So what do I mean by this sort of unique model of innovation? Well, somewhat unique, certainly for a UK university, is that we have a team of engineering staff, industry experience engineering staff and commercial staff who sit alongside our academic research team. And their role is to support the work of the academics, to help with research translation. And this allows us to undertake rapid response projects in collaboration with industry, as well as longer term research projects with our industry partners. And the team then help to develop proof of concept demonstrators based on our research output as the first steps towards commercialization. So in terms of within our institute, our focus is looking at the underpinning technologies that are needed to secure complex systems, looking at security of devices, to securing the communications between devices, right up to securing the information garnered from devices and stored in the cloud. So we look at a range of activities from things like trusted hardware, looking at malware detection, resilience in industrial control systems, and then looking at all the way up to kind of things looking at AI for cybersecurity, security for AI, and autonomous security as well. So we also have an industry membership program. So we have a small number of full member companies who pay to be part of our program and sit on our advisory board and also influence and help to inform our research and development roadmap. And then we have associate members who we also collaborate with in sort of I suppose, less significant or more on a smaller contract and project basis. And these obviously change quite more regularly, I guess, than our full member companies. And then to say as well that the Institute also has a lot of activity in the innovation space, and we do a lot of work in supporting startups, scale-ups, and SMEs working in the area of cybersecurity in partnership with a number of other organizations. So we run a cyber runway program in conjunction with Cylon and Deloitte, supporting a range of activity in this space. And then a really good example of some of the work that we do in this area has been the work we did as a delivery partner on a £13.5 million UK government-funded acceleration programme called LORCA, standing for the London Office for Rapid Cybersecurity Advancement. And this was alongside Plexel and Deloitte, and based in the Here East site at the original Olympic Park site in London. And our role within this work was to provide academic masterclasses to cohorts of companies coming through, and also to provide engineering support through our engineering team. So over the past 3 years, 72 cyber scale-ups joined the LORCA programme, and they have raised over £200 million actually in investment and created over 800 jobs since that time. So it's been really successful to date, and we're currently in the stage 2 of this. We're calling it LORCA Ignite, where we're taking a number of those projects even further along in their journey. And then finally, in terms of our institute, we've been a critical factor in establishing Northern Ireland as the UK's leading cybersecurity cluster. So from a standing start back in 2009, where the CSIT was formed, we've grown the cyber sector in Northern Ireland to now employing over 2,300 people across 104 companies, generating £110 million in salaries each year. So the range of companies is from, again, supporting those sort of startups and scale-ups, but also we've helped to attract much larger companies, the likes of PwC and Deloitte, who now actually have their major cybersecurity, UK cybersecurity teams based in their Northern Ireland offices. So it's been hugely successful and is continuing to grow. So coming back then to the title of my talk today, which is looking at securing connected devices and challenges and opportunities. So back in 2018 now, Tech Republic released a list of the 11 or so least secure connected devices. And not surprisingly, it included devices like smart locks, interactive toys, connected cars, wireless medical devices, your overlooked office devices, so connected coffee machines and so on, and things like smart baby monitors. And obviously, if an attacker compromises any of these devices, they can gain internal access to your network, and all your information will be at risk. So what we're seeing, obviously, in the last 5 to 10 years is a significant increase in the number of attacks against these types of IoT devices, and it continues to increase year on year. So for example, particularly we're seeing now malware designed to specifically attack these types of devices. So back in 2016, I'm sure many of you are aware of, we had the Mirai botnet, which targeted in the end over 100,000 IoT devices, were compromised for use in a massive distributed denial of service attack against DIN, which disrupted US internet traffic and quite a number of the significant and major services such as Amazon and Netflix, Twitter, and BBC, and so on. And then we've seen variants of this more recently. So then in 2018, we had the hide and seek botnet. And again, it was able to spread very rapidly across IoT devices, using custom built sort of peer-to-peer communication to try and exploit those devices. And I suppose a little bit, we've seen again variants of those, but more recently in the last few years, we're actually seeing new malware being developed, again targeting these types of devices, and now coded in Go, so the language developed by Google. And this is actually sort of a new malware built from scratch, and again relying solely on brute forcing its way into IoT devices. So in recent research that's actually looking at the scale of these types of attacks on IoT devices, this is really, really a global scale. And in particular, China and Brazil are host to the highest number, or currently, or as of April 2020, host to the highest number of compromised IoT devices. So then OWASP released a list of what it believes to be the top 10 vulnerabilities that make IoT devices insecure. And, I'm not sure if you can kind of read this in some detail, but this includes things like weak passwords or hard-coded passwords, insecure network devices and insecure sort of interfaces to devices and like sort of APIs and so on, lack of appropriate security update mechanisms for some of these devices, and the use of outdated components within the devices or insecure components. Insufficient privacy protection is another major issue on any information stored on devices, and insecure then data transfer between devices. We're also listed here as the lack of device management or appropriate device management for devices. And a very obvious one is then around insecure default settings, where many of the attacks in terms of malware types of attacks are targeting because of the kind of default settings that are shipped with devices. And then the final one, number 10, looks at the lack of physical hardening and physical security of the devices themselves. So certainly over the last or over recent years, and in particular the last 5 years, we're seeing a lot more guidance, standards, policies, processes now being put in place that are starting to deal with many of these issues, and particularly around things like insecure password guidance, dealing with insecure default settings, and requiring now that all manufacturers ensure that more secure default settings are put in place for devices. But the focus of our research has been on new technologies that are helping to address IoT security, and looking at issues in particular around things like the physical hardening, looking at access control vulnerabilities, and the privacy protection of information stored on devices. And then another major factor that I suppose can't be overlooked is then the recent vulnerabilities that are actually affecting, I suppose, the underlying hardware itself. And significantly the work that's been done on microarchitectural attacks. So back in 2018, we had the introduction of Meltdown and Spectra, with Meltdown exploiting the out-of-order execution to leak target's physical memory, and Spectra looking at taking advantage of the speculative execution using branch prediction. And all of these attacks, again, targeting microprocessors, really meant that billions of devices that were affected, significantly because they attacked not just sort of one particular microarchitecture, microprocessor, but Intel, AMD, ARM microprocessors were all vulnerable to these types of attacks. And then more recently, we're coming to then, like the last example I have here is Crosstalk, where again, this is looking at the possibility of attackers being able to leak sensitive information now from across cores on many Intel CPUs. And this is then being able to bypass some of the countermeasures and mitigations that have been put in place against some of the Meltdown and Spectre types of attacks, where it was assumed that it was kind of more targeting sort of different cores. And therefore, this can now, this crosstalk attack can now thwart those mitigations. So again, a serious challenge in terms of trying to understand how to build better protection for IoT devices. And then finally, in terms of some of the major issues, what about if we think about an internet of cloned things? So obviously with the globalization of supply chains, we now have the use of overseas boundaries, third-party IP, third-party test facilities, and with so many different untrusted entities now involved in the design and assembly phases, it's becoming increasingly difficult to ensure the integrity and the authentication of electronic devices. So supply chains are now susceptible to a range of hardware-based security threats, from things like hardware Trojans, IP piracy, reverse engineering, cloning, and things like side-channel attacks. And again, a recent report published by Europol and the EU Intellectual Property Office in the EU are saying now that counterfeiters are actually now exploiting the current global supply shortage in semiconductor chips and starting to use these issues to help bring more counterfeit goods and cloned devices into the supply chain. And obviously with counterfeit devices, they can much more easily then host malicious software, firmware, or hardware. And I suppose more worryingly, due to the nature of the counterfeiting industry, it's actually very difficult to ascertain the true extent of the problem. So then if we're trying to then look at the challenges with IoT devices, what are the challenges when we try to look at, well, how can we provide security in connected devices, and what challenges do we face? So first of all, obviously, connected devices and IoT devices tend to be lightweight, low power, quite cheap devices, and cryptographic algorithms that are typically used to provide security can often involve computationally expensive operations. And in particular, if we think of wanting to provide authentication, we would need to use public key cryptography, which is quite computationally intensive and therefore expensive to implement. So how can we go about implementing these complex cryptographic processes? And actually today with now with the post-quantum cryptographic processes that are even more computationally intensive, is it possible to achieve what you need on very resource-constrained devices to help protect data and help protect the authentication of devices? And then a further issue then is the fact that adversaries typically then have physical access to connected devices and these types of devices to perform attacks. So things like side-channel attacks become much more easy for attackers and can be used to extract secret keys from the devices using a range of techniques from power consumption, electromagnetic emanation, timing analysis, and even acoustics to uncover the secret key used on devices. So to give a very simplistic, I guess, a simplistic example of this, one of today's most secure cryptographic algorithms from a mathematical point of view is obviously the RSA algorithm. Just to show how easy it can be, one of the main functions within this is square and multiply algorithm within RSA, and it's directly includes the secret key value within this algorithm. So it uses that in this loop down here. So if your key value is a 0, then you perform a squaring, and if it's a 1, you perform a squaring followed by a multiplication. So then actually it's possible to then identify that by simply monitoring the power consumption. So if we implement the basic RSA algorithm on a device and monitor the power consumption, the power profile of these different operations, or these operations, the square and multiply, are actually different, and therefore it's very easy to see when your key bit is either a 0, where you'll have a square on its own, and then a 1 where you'll have a square followed by a multiply. And simply then by looking at that power consumption profile, you can read the key, the secret key, directly from that information that's leaked. So then so we need to, obviously in terms of today's devices, it's RSA is not used in its native form. Sorry, I've got a visitor. Off you go. I'm going to talk. Go. Close the door. So in today's devices, RSA isn't implemented in its sort of native form, obviously for this reason, and it has some protections, but there are still a lot of challenges in terms of mitigating against side channel attacks which I'll talk about a little bit later on in my talk. So if then a further challenge then, as I've already mentioned, the idea of post-quantum cryptography being complex to implement, we kind of think about what if quantum computers become a reality in the future, and it's maybe if and when, but quantum computers become a reality. Well, actually, commonly used public key encryption algorithms will be vulnerable to Shor's quantum algorithms. So, for example, RSA and elliptic curve cryptography based techniques are based on integer factorization and the discrete log problems. So Shor's algorithm can solve both problems at exponential speed over today's classical computers. So therefore, this means that with quantum computers, it'll be possible to break all of today's security systems, which the majority of which use public key processes. And if you think about IoT devices, they typically have a secure boot mechanism sort of baked into the silicon that cannot be upgraded. So that will leave many of those devices vulnerable to quantum attacks in the future. So I guess, when I talk about this, often it's asked, well, what is the likelihood of such an attack, or what, when will quantum computers become a reality? So Michel Mosca, who is an expert in quantum cryptography, where he works at the Institute for Quantum Computing at the University of Waterloo. In the last few years, he has looked at releasing a report on the quantum threat timeline. And the most latest report looks at what the experts in this area, their estimates of the likelihood of a quantum computer being able to break RSA 2048 in 24 hours. And this is quite interesting, and that the most recent report really suggests that most experts think that this is fairly likely to happen within the next 10 to 15 years. So it's really, I guess, not that far away. And obviously in the US at the moment, the National Institute for Standards and Technologies, or NIST, is just finalizing their standardization process, looking to select new post-quantum or quantum resilient algorithms that are resilient to quantum attacks, such as Shor's algorithm. And those will be standardized in the next 2 years or so, and open them for adoption for companies. So in terms of then looking at, well, in terms of all of these challenges and so on, then in terms of our research at CSIT, what we're trying to do is looking at addressing the security of future connected devices, and what can we do to better address this problem, and things like the physical hardening of devices and privacy protection and so on in terms of research. So the first area we look at is an area called Physical Unclonable Functions. And for those who may not be maybe aware of what this is, a physical unclonable function, or PUF, is a digital circuit that uses manufacturing process variations to generate a unique digital fingerprint. So when a PUF circuit is implemented on a device for any given challenge, a unique response is generated. And so even then, if the same PUF circuit is implemented on a second device, identical to the first device, and for a given challenge, again, another unique response is generated. So therefore, no two chips will give the same response when supplied with the same challenge. So you're effectively creating that unique digital fingerprint from electronic devices that's picking up on those unique underlying manufacturing process variations. So it's really, really quite clever technology. And then the applications then are things like, in terms of anti-counterfeiting, anti-tampering, and things like unique key generation for devices, and then lightweight authentication and unique identification procedures for lightweight devices. So some of the work that we've been doing have been looking at over many years, have been looking at various physical unclonable function designs, and how can we use this technology again in applications to sort of try and solve some of the challenges. So we've been looking at both memory and delay-based PUFs, and the first one here that I'm showing is some work that we did on memory-based PUFs, or sorry, delay-based PUFs. where really a delay-based PUF is really looking at creating a race condition between the delay paths of variability sensitive circuits. And then to maximize that variation and to avoid any sort of bit aliasing that can occur, the wiring paths must be placed and routed as symmetrically as possible to minimize any nominal delay difference that can kind of appear between two paths. So if there, as we do, if we're working with FPGAs, that can be accomplished by manual routing and timing analysis of your design. So for example, in our very lightweight design, which we call a PicoPUF, to generate a 1-bit response, authenticated response from a device, we use 2 flip-flops and 2 cross-coupled NAND gates. And then the timing of the 2 delay lines in the sort of the higher delay line and the lower delay line in the circuit here will differ. So if they're manually placed en route to be identical in terms of length, but they will actually differ in terms of the timing due to the underlying manufacturing variability. And that's what you're trying to pick up and detect in terms of producing your response. So to generate then a 128-bit response, it will cost you, so we've looked at implementing one of these circuits. So for a 1-bit response on a slice within an FPGA device, for example, in this case, we're showing a Spartan 6 device. So to generate 128-bit response, it will cost you 128 slices. So it's quite minimal in terms of the hardware area and the hardware resources, and even less, for example, on other devices. So we've also done work where you've actually shown how you can, this example is just this circuit implemented within one CLB, but we can actually fit more than one of these circuits within a CLB as well. So again, it's just very minimal footprint in terms of design. So again, ideal for sort of lightweight and those connected devices. So in terms of how this performs, well, one of the advantages of this is due to that balanced routing approach, achieves very high uniqueness across. So in terms of what you're looking for is that this will achieve a unique response on every device that you implement on it. So we have a large test bed of devices that we use in our research, and you're looking for we look to measure in terms of uniqueness and trying to understand that metric. You look at the inter-chip sort of Hamming distance, and you're looking for a metric of 50%. So we can achieve very high uniqueness value from this particular design. And then in terms of reliability, obviously, because you're picking up on underlying manufacturing process variation, you really need to ensure that it's resilient and reliable against environmental variations, things like temperature changes, any sort of voltage changes and so on. And obviously you need it to be 100% reliable. So again, in terms of this particular design, we achieve very high reliability results with it as well. And this picture just shows, again, one of the proof of concept demonstrators that our engineering team helped to build based on this research work. So then the other sort of main sort of area within PUF designs is memory-based PUFs, and this is kind of typically looks at looking at your response from the measurement of startup values, for example, in memory cells. So that's a typical, it's called an SRAM PUF, for example. But we've been looking at PUF based on DRAM memory, and DRAM cells are gated capacitors. So the manufacturing process variation is really in the rates of charge and discharge, and that's then our entropy source that we're trying to detect here. So we generate a hardware-rooted ID through controlled read errors. And this is a very intrinsic PUF, so there's no additional hardware, and we use only sort of commodity hardware devices with no modifications to test the designs. So we can generate very, very quickly generate large, reliable identifiers from DRAM PUF. And our challenge in this case will be a set of timings plus the memory locations to read, and then the response is that error pattern. So in this case, we did a proof of concept demonstrator. So this was a particular project we were involved with. So we did a proof of concept demonstrator on Linux desktop systems and achieved significant speed up improvements in terms of the design and the protocol approach that we used for this over previous work and kind of the area. We achieved near ideal uniqueness with the responses that were developed in terms of how it's unique digital fingerprint on different devices. And again, in terms of the metrics we did in terms of measuring temperature variations and so on, again, very, very highly reliable design and result. So some of the work then we've done, as I say, in terms of different PUF designs, including those that I've just talked about. As I say, we've developed proof of concept demonstrative of these, and then in collaboration and co-creation with a number of industry partners, we've looked at translating this technology into a range of application scenarios. So for example, we did some work with LG CNS and ETRI in South Korea on translating this into evaluating work around for anti-tampering of EV charging systems. So tamper-proofing some of the components within their charging systems. We also looked at it for enhanced authentication of smart meters in another project. And then also with a company partner looking at using this technology in electronic component anti-counterfeiting. And we're still very much actively researching, collaborating with industry partners in this area, and still ongoing research to be had. So then, in terms of then other work that we can do and what we are doing to address some of the security challenges is in the area of side-channel analysis. So as I mentioned earlier, side-channel analysis can be used to extract secret keys from devices using things like electromagnetic emanations and timing analysis and so on, or power consumption. So what we're doing in our research is investigating both new attack techniques as well as low-cost countermeasures to protect sort of embedded devices against attack. And obviously, in terms of really understanding how you can develop countermeasures, you need to understand the capability of attack approaches. And many SCA-based or side-channel attack theory-based approaches to date, have been based on differential power analysis and correlation power analysis, and these have been well known. But more recently, we're starting to see a machine learning and how it can learn from the side-channel information to actually reveal the secret key of a cryptographic device. And one of the challenges with machine learning is that actually it can bypass some of the mitigations that are already in place in devices to protect against some of the more traditional side-channel attacks like differential power analysis and the correlation power analysis attacks. So we did some early work again using a novel sort of neural network-based profiling attack against a masked sort of smart card implementation of AES, and again proposed the use of a pre-processing step to using PCA to just significantly increase the success of that attack. And we developed a classifier that not only correctly then identifies a mask that's used to kind of help mitigate against previous types of attacks. So it bypasses that countermeasure. And then once that's removed, either you can then, perform your traditional attack, or again, simply use the machine learning approach to continue on to uncover the secret key. And then more recently, we've been looking, I suppose, at more sort of deep learning based attacks. So we proposed a convolutional neural network based approach. And this actually uses sort of plain text as an additional feature to the input of this attack. And again, I'll not go into the detail on this, just more to give the high level, but very happy to speak to anyone who's interested in the topic. But using that plain text as that additional feature, we can reveal the secret key again from sort of protected devices that have mitigations in place against traditional side-channel attacks. Using that machine learning capability, we're able to reveal the secret key with just two power traces from the device. So these can be very, very sort of, I suppose, easy attacks. Again, and it shows really the capability of machine learning approaches. So with this technology, we're currently still at the attack stage, but also more recent research has again been looking at, well, actually, how can we use some of the capability here to then look at mitigating against these types of machine learning attacks? And we're looking at a number of approaches at the moment in that area. So another topic that we address is hardware Trojan detection. And again, using some machine learning and deep learning based approaches actually to help with this. So, hardware Trojans are obviously malicious modifications to ICs, to integrated circuits. And again, as I mentioned, with that globalization of the semiconductor supply chain, it's becoming more difficult to ensure the integrity and authenticity of devices. And one of the approaches we're looking at is, well, what can we do more targeting that design phase to ensure that at that phase, in terms of having different third-party IPs and so on, that we can trust the designs. So taking advantage then of machine learning based methods, we have been looking at those approaches in terms of helping to design harder Trojan detection approaches in more recent research. So so in terms of, some of the work again that we've done in this area is looking at a range of approaches. So first of all, looking at things like pre-processing of the net list. So, really the use of machine learning is quite new in this area. So it's like, well, how can you translate this into this problem into something that we can address with these new techniques? So we've looked at a novel sort of net list information extraction strategy, and then using NLP or natural language processing techniques that can help in terms of information encoding. And then those encoded feature traces can then be input into your more typical sort of deep learning based classification models. So using things like LSTM and the convolution neural network models, and then using those approaches in terms of providing that harder Trojan detection. Our training and testing for this are based on, obviously, as I said, this is I suppose you won't get companies to provide you with information on harder Trojans that readily. So we're using open sourced harder Trojan benchmarks. So we're using the Trust Hub libraries and benchmark circuits for the research that we do. And again, using this approach, we're actually able to achieve very, very promising detection results, harder Trojan detection results for both combinational and sequential harder Trojan circuits. So to the best of our knowledge, some of this work is probably the first detection system that really is based entirely on deep learning approaches. And it's a sort of a data-driven detection approach. So it can detect harder Trojans without the author having to have any prior knowledge of really the circuits. So really the idea for this is, that we can embed some of this technology and some of these into tools and into EDA tools, so that designers don't need to have the expertise in all of these areas, but can run these tools to very quickly check if the designs that they're incorporating into system on chips have harder Trojans or not. So another area then as we're looking at is, as I talked about, the issue with post-quantum cryptography, and this will be the last area of research that I talk about. And this is obviously mitigating against the potential for quantum attacks and the attacks from things like Shor's algorithm. Move on here. So firstly, just to speak to, again, we've been looking at this area for quite a number of years, and we hosted a major European Horizon 2020 project on this topic started in 2015 and finished in December 2018. And this was actually around the time that it was 2015-16 that NIST actually started its standardization, or launched the standardization process for new post-quantum techniques. But this particular project, again, was really to look at, because these new approaches to creating quantum resilient cryptographic approaches are much more complex than today's classical RSA and elliptic curve approaches. Actually, are they practical or sufficiently practical for us to be able to use them in practice in future ICT systems and applications? So there are a number of different approaches that can be that can be targeted. In this particular project, we targeted lattice-based cryptography, and we worked with a number of consortia partners and industry partners, you shall see on the bottom of the screen here. And with our industry partners, IBM, Thales, and an SME in the UK called HW Communications, we looked at developing practical solutions for a number of areas, one of which was targeting sort of IoT devices. So as I said, really the idea behind post-quantum cryptography is that it aims to build crystal systems from classical problems. These are not quantum-based approaches, the classical problems that are used, but for which there is no known way to recast that problem in a quantum framework. As I say, there are a range of approaches that can be adopted, so code-based, hash-based, multi-rate quadratic signature schemes, and also, as I say, lattice-based cryptography. And lattice-based cryptography is really looking at based on shortest vector or closest vector problems. Finding the shortest vector in a high-dimensional random lattice is a well-known challenging task, and that's believed to be hard even for quantum computers. So from that sort of underlying hard problem, we can then build cryptographic approaches that we can use for encryption, authentication, and indeed advanced techniques as well. So as I said, the NIST competition launched in 2016. As I say, draft standards are due, we're due to hear the announcement anytime, and draft standards will be developed in the next 2 years. This particular consortia that we led, we're involved in 3 of the submissions, all lattice-based approaches, and have all made it through all of the different rounds of the process, I've made it through to the final stages. So very, very, very I suppose hopeful and expect that certainly lattice-based cryptography is a really key contender here as a post-quantum standard going forward, and indeed one of these schemes will be chosen. So kind of in terms of summarizing some of the outcomes of the work that we did, we developed some practical hardware and software implementations of some of these lattice-based approaches in terms of both authentication and encryption, and some, as I say, advanced cryptographic primitives, so things like identity-based encryption, authenticated key exchange. And we also looked at building in resistance to these designs to side-channel attacks. And one of the target areas was on resource-constrained devices, and looking at not only just in terms of the performance, but also, as I say, well, can we also build in resistance to side-channel attacks and still deliver this on resource-constrained devices. And so, as I say, with one of the partner companies, in this case, it was the SME in the UK, we looked at being able to use a lattice-based approach for smart tag systems, where we were implementing some of the approach in terms of obviously trying to keep some of the more computational aspects of the approach to the reader side of the system, but also being able to implement some of the complexity within the tags themselves, and obviously with the limitations that impose, we were able to successfully show a scheme that delivered that for those kind of devices. So, really it is achievable for IoT devices. And then more recently, we've been looking then at really demonstrating hybrid quantum safe solutions. So this is in collaboration with Toshiba, where we're combining some of the quantum key distribution, so quantum cryptography, with some of the post-quantum cryptographic algorithms. So obviously in terms of being able to provide our authentication piece, we need to be able to use some of these post-quantum classical approaches. And we've been able to implement one of the lattice-based schemes, so the Kyber scheme, as part of the NIST competition, into an overall sort of hybrid quantum key distribution system, and again successfully demonstrating that. Again, this is probably somewhat way off from being able to target resource-constrained devices, but again, there's again very significant leaps in terms of the whole quantum technology space, and a lot of research targeting quantum cryptography, targeting sort of more lightweight and more efficient devices as well. And another project we look at again is in the UK. We have a major sort of quantum hubs in the quantum space. So we're part of the UK Quantum Communications Hub, and again looking at developing very efficient post-quantum digital signature designs, and the exploration of this idea of exploring these hybrid, very efficient hybrid post-quantum QKT designs. And in this project, we then also look at that security piece. So what are side channel attacks? How do we build resilience into that, into these sorts of hybrid systems as well? Okay, so to conclude my talk, I guess for the true potential of connected devices to be realized, in terms of the fact that in terms of being able to enable the ubiquitous nature of IoT, we have many billions of these devices now in the world, and if we want to get the true potential of those and gain from the advantage that they can offer to society, we really need to ensure that security is built into those devices from the outset of their design, and that it's not as an afterthought. Now, as I said earlier, in terms of the 10 vulnerabilities within IoT devices, standards and policies and guidelines are emerging to mitigate against certain vulnerabilities. So things like default settings, weak passwords, updates, etc. But technologies can also help, and that's where our work and our research have come in terms of helping with things around the physical hardening, with the data protection and the data privacy, and providing authentication of the devices, but also securing that sensitive data on those devices. So I've talked about some of the technologies that we're looking at in terms of physical unclonable functions, for anti-counterfeiting, for unique ID generation, and also authentication, or very lightweight authentication for some of these devices. I talked about the need to develop things like machine learning based countermeasure or side-channel attack countermeasures, and some of the work we're doing in terms of the attack approach, first of all, in that space. And then looking at machine learning based hardware Trojan detection. So to start looking at terms of the EDA tools, and what can we do at that stage to try and detect things like clone devices at a much earlier stage. And then finally, I talked about our work on lightweight quantum resilient cryptographic solutions. And as we move towards with the NIST standards coming through in the next 2 years, and as we move towards the potential for quantum computers becoming reality and what that means for cryptography, then we will certainly see that again, IoT devices will certainly be vulnerable, and we'll need to ensure we have appropriate lightweight quantum resilient solutions that are available to support that. So finally, the security of connected devices can be regarded as just one layer of a connected infrastructure. However, certainly secure connected devices are critical to all of this, and a step change in the security and privacy of all layers of connected systems is needed to ensure the usability acceptance of it all. But as I say, those secure connected devices are absolutely critical, as they can provide the root of trust for your entire system. So just to finish, this slide really just shows a number of our more recent related publications for some of the work that I've talked about. Certainly visiting our website will provide a wider or more extensive list of publications if anyone is interested. So that completes my talk, and I'm very happy to take any questions.
Well, we have one in the Q&A, so can you see that?
Yeah, let me read it here. So to what extent can post-quantum cryptography be a drop-in replacement for public key? And what are the main differences from a tool user point of view? Okay, yeah, so certainly in terms of the work that we've done to date in terms of post-quantum cryptography, it absolutely can. So yes, it is somewhat more complex than the likes of RSA and elliptic curve cryptography, but actually in terms of that particular the post-quantum or the lattice-based cryptographic approaches, some of the algorithms are actually proving to be very, very efficient to implement on devices, and certainly on some resource-constrained devices. So certainly this is one factor in the NIST competition one of the factors, as well as obviously the security of any new algorithm being developed, one of the other aspects for the selection of the candidates is that how practical they are across a wide range of platforms. So they are looking at how efficient they are in terms of implementation. So certainly there have been a number of examples of where these are now starting to be evaluated and used within protocols, within today's schemes and applications as replacements to public key. So you will see much more of this. Certainly once the standards are in place in the next 2 years. I guess there is a little bit of reluctancy for some companies to start adopting some of the approaches just yet, but there's certainly already been some examples where it has been. So it certainly is at the moment there are certainly solutions that can provide that sort of replacement for public key. In terms of the challenges, I guess the main challenge will be the main challenge with the implementations, and I guess from a tool user point of view, is really in relation to the key sizes. So this is the most significant differential, I guess, from your classical approaches. And again, within the work that we've done in the project, we had to work with companies because for them that key management aspect is a lot more complex with the post-quantum approaches than what it had been previously for classical, due to the significant sizes of your keys that are used in those. So I would guess that is without a doubt the main challenge. In terms of other difficulties, in terms of building and side channel resilience, I don't see any significant difference over what you would have to do for classical approaches over the post-quantum approaches.
All right. So we've got that one. The next one's just a comment. A compliment, actually.
I will take that. Thank you very much.
It was a great talk. You really sort of covered the landscape there. So an interesting issue here, perhaps. We have some undergraduates who take this class or tune in. Are you interested in prospective grad students there?
Absolutely, very much open to welcoming any students who are interested in joining. We would have some open positions, and we're currently waiting actually on on the outcome of a grant that we expect very, very soon, which will open up actually a large number of studentships for graduate students. So certainly, if anyone is interested, please do certainly get in touch with me or keep an eye on our website, and those opportunities hopefully will appear very, very soon.
So I'll tell the audience that we have a research relationship, CERIAS with CSIT, and I expect that we'll have some ongoing collaborations and opportunities for anybody who's interested in pursuing that. I wanted to ask, you don't have another question in the Q&A, but this closing picture as a shipyard with a dry dock, is the university located there, or is this just
Yeah, so yeah, good question. So actually where we're based, CSIT is actually not based on the main university campus. We're based on our kind of our science park within Belfast, and this actually this part here is actually the dry dock from which the Titanic ship sailed. So this is the Titanic quarter of Belfast, and this building here in the green, if you can see the laser pointer on that, is actually where CSIT is based. So we face on to the dry dock from where the Titanic was set sail. And what's just off the picture, outside of the picture here, is that there's a pump house, the original pump house that was used to I suppose help that, or pump water in and out of that dock during the time when the Titanic was built.
Well, I hope that companies don't view it as somehow prophetic that you are launching startups next to the Titanic's dry dock.
So what we normally promote is the great feat of engineering, which is the building of the Titanic was in Belfast, but also many other ships. So these two cranes here are also very synonymous with the Belfast skyline, so much so that they have their own nicknames, Samson and Goliath. And still today, there's a lot of work that goes on in that shipyard in terms of repairing of ships and other activity. So we would say that we have gone from ships to chips within our institute in terms of the work that we do.
Yeah, I see White Star House. So is that the White Star Line? Is that still in existence as such?
So that's coming. That's named after that, but that's actually, again, major companies. So one of the reasons that we set up down on the science park was to more closely link with industry partners. And there's also one of the buildings here is set up as it's an innovation center. So it's set up to house startups and spin outs. So we also have space within our building to support that activity as well. So we would work very, very closely with a number of the companies that are based within the buildings around this. And even this is now already, this picture is already out of date because there's quite a number of other new buildings. So this whole area is being redeveloped. So when we moved to this building first, our building was literally the first building on this sort of brownfield site. And it's already had significant development over the last few years even. So it's quite an exciting time to be in the area.
Yes. Well, you can also argue or tell people that White Star also produced the Britannic and the Olympic, and they did
exactly.
They met unfortunate ends, but not the same way. So
yeah.
No, that's wonderful, and I do hope to visit there in person sometime, and some of our colleagues here at Purdue to take advantage of this ongoing relationship that's been made available. In the time here, while I was making those somewhat unjust comments, but I haven't seen any other questions appear in the Q&A. So it was a very thorough presentation. I think you covered a lot of the points. I couldn't think of a good question that I wanted to ask. So I think this is a good point at which we'll bid you a good evening. You're, I believe, 5 hours ahead of us. So we very much appreciate you staying up and making this presentation to us. And to everyone who's listening in following the seminar series, we will resume in the summer, probably, and I don't have the date exactly, you'll have to look on the website, but we're going to have probably an every other week set of presentations in the summer, of a somewhat slower pace than during the academic year. And then in August, when the academic semester starts up again, we'll resume our once a week seminar series. So these are all available online through our website, through iTunes, through YouTube. We welcome people to view those, and for those of you who are facing them, we wish you the best of luck with your finals. And if you're graduating, maybe you'll come back and visit our seminar series from wherever you are after you leave Purdue or wherever you may be. So with that, thank you very much. Thank you, Professor O'Neill, for concluding a wonderful seminar series here for us this semester. And thank you to everybody for attending.
Thank you all.
Bye-bye.
Thank you all. Bye.